There is a boundary, not a wall of brick or steel, not a fence of wood or wire, but a boundary nonetheless. It is the limit of our sight, the horizon of our understanding, the edge of everything we can ever know. For centuries, humanity looked up at the night sky and wondered what lay beyond the stars. We imagined gods, we imagined monsters, we imagined nothingness. But in the last century, we built machines. We built eyes of glass and mirror, sensors of silicon and gold, and we launched them into the void. We pointed them away from Earth, away from the sun, away from the safety of our own solar system, and we looked into the deep dark. And what we found there changed everything. This is not a story about aliens. This is not a story about science fiction. This is a story about data. It is a story about photons that have traveled for billions of years to strike a sensor, carrying with them the history of creation. It is a story about what NASA saw when it looked at the edge of the universe. But here is the first mystery we must confront. Does the universe actually have an edge? When we speak of the edge, are we speaking of a physical barrier, a place where space simply stops? Or are we speaking of a limit of light, a horizon beyond which information cannot reach us? The answer is more strange than either option. The edge we see is not the edge of space itself, but the edge of time. It is the limit of how far back we can look. And yet, within that limit, within that observable sphere of light, NASA has found anomalies. It has found structures that should not exist. It has found movements that defy explanation. It has found a cold spot in the background radiation of the cosmos that suggests something lies beyond our view, something pressing against the bubble of our reality. To understand what was seen, we must first understand the instrument of sight. We must understand the nature of light itself. Light is not just illumination, it is a messenger. It is the only courier we have from the deep past. When you look at the sun, you see it as it was 8 minutes ago. When you look at the nearest star, Proxima Centauri, you see it as it was 4 years ago. When you look at the Andromeda galaxy, you see it as it was 2.5 million years ago. The further you look, the further back in time you see. This is the fundamental principle of deep space astronomy. There is no way to see the present state of a distant object. We are forever looking into history, and so, when NASA points its most powerful telescopes at the faintest, most distant glimmers of light, it is not looking across space. It is looking back to the beginning. But there is a limit. There is a point where the light stops, not because there is nothing there, but because the universe was once opaque. Before a certain time, the cosmos was a hot, dense fog of plasma that scattered light in every direction. Photons could not travel freely. They were trapped in a prison of particles. It was only when the universe cooled enough for atoms to form that the fog lifted and light was allowed to stream freely for the first time. This event is called recombination. The light from that moment is still traveling through the universe today. It is the cosmic microwave background. It is the oldest light we can see. It is the wall behind which we cannot peer with traditional telescopes. This is the true edge of the observable universe. It is a wall of fire, cooled by expansion into a whisper of microwaves. But what lies behind that wall? What lies before the light? And what lies beyond the sphere of our observation? These are the questions that drive the scientists at NASA. These are the questions that keep them awake at night. Because when they map this background radiation, when they chart the distribution of galaxies, when they measure the expansion of space, they find things that do not fit the model. They find a universe that is stranger, colder, and more complex than we ever imagined. They find hints of a multiverse. They find hints of cosmic collisions. They find hints that our observable universe is just a small patch of a much larger, much darker reality. In this narrative, we will journey through the data. We will walk through the discoveries. We will examine the images captured by the Hubble Space Telescope, the Planck satellite, and the James Webb Space Telescope. We will listen to the static of the cosmic microwave background. We will trace the gravity wells of the Great Attractor. We will investigate the cold spot. We will explore the theory of inflation. We will confront the dark flow. And we will ask the ultimate question: if we can see the edge of the observable universe, what is looking back at us? The journey begins not with a telescope, but with a realization. The realization that we are trapped. We are trapped on a rock, spinning around a star, in a galaxy, in a cluster, in a supercluster, in a universe that is expanding faster than we can travel. We can never leave our observable bubble. We can never see what lies beyond the horizon. And yet, through the subtle distortions of gravity, through the faint echoes of the Big Bang, through the mathematics of geometry, we can infer what lies there. We can feel the shape of the room even if we are blindfolded. This is what NASA has done. They have felt the walls of the universe, and what they felt was vibrating. Chapter 1: The Boundary of Sight. To speak of the edge of the universe is to speak of a paradox. In our daily lives, an edge implies a termination. If you walk to the edge of a cliff, there is ground and then there is air. If you walk to the edge of a table, there is wood, and then there is nothing. We expect the universe to have a similar boundary. We expect that if we could travel far enough, fast enough, we would eventually reach a point where space ends. Perhaps there is a void beyond it. Perhaps there is another universe. Perhaps there is simply nothing. But the mathematics of general relativity, the framework upon which our understanding of gravity and space is built, suggests something different. The universe may not have an edge in the way we understand it. It may be finite but unbounded, like the surface of a sphere. If you walk on the surface of the earth, you never fall off. You never reach an edge. You just keep walking, and eventually you return to where you started. The universe could be like this, but in 3 dimensions: a hypersphere. However, this geometric possibility is distinct from the observable universe. The observable universe is defined not by geometry, but by causality. It is defined by the speed of light. The universe is approximately 13.8 billion years old. Light travels at a finite speed. Therefore, the furthest we can see is the distance light has traveled in 13.8 billion years. But because space itself has been expanding during that time, the objects that emitted that light are now much further away. The current distance to the edge of the observable universe is about 46 billion light years in every direction. This creates a sphere around Earth with a diameter of 92 billion light years. This is our cosmic horizon. Anything beyond this horizon is invisible to us, not because it is dark, but because the light from those regions has not had enough time to reach us yet. And because the expansion of the universe is accelerating, driven by dark energy. some of that light will never reach us. Galaxies beyond a certain point are receding from us faster than the speed of light. This does not violate relativity because it is space itself that is expanding, not the galaxies moving through space. But the consequence is profound. There are regions of the universe that are causally disconnected from us. We can never interact with them. We can never see them. They are, for all intents and purposes, separate universes, even if they are part of the same physical continuum. When NASA scientists speak of the edge, they are usually speaking of this observable horizon. They are speaking of the limit of data, and within this limit, they have mapped the cosmos with increasing precision. They have cataloged billions of galaxies. They have measured the distribution of matter. They have constructed a three-dimensional map of the local universe. But as they pushed the boundaries of this map, as they looked further and further out, they began to notice inconsistencies. The universe is supposed to be homogeneous and isotropic on large scales. This is the cosmological principle. It states that if you look at a large enough volume of space, it should look the same in every direction. There should be no preferred direction. There should be no special places. But the data suggests otherwise. There are structures that are too large. There are flows of matter that are too coherent. There are temperatures that are too cold. These anomalies cluster near the edge of our observation. They hint that the cosmological principle might be broken. They hint that our location in the universe might not be as average as we thought. Or they hint that the universe beyond our horizon is influencing the universe within it. Gravity, after all, does not stop at the horizon. The gravitational pull of matter beyond the observable edge can still affect the matter inside. We cannot see the source of the gravity, but we can see the effect. This is how we know something is out there. This is how we know the edge is not empty. Consider the concept of the particle horizon. This is the maximum distance from which particles could have traveled to the observer in the age of the universe. It represents the boundary between the observable and the unobservable. But there is also the event horizon. This is the boundary beyond which events will never be observable, even if we wait forever, because the space between us and those events is expanding too fast. We are losing access to the universe. Every second, more galaxies slip beyond our event horizon. They disappear from our future. The edge of the universe is not static. It is shrinking in terms of what we can ever hope to reach, even as the observable sphere grows in terms of what light has reached us. This dynamic boundary creates a sense of urgency in cosmology. There is a window of time in which we can study the deep universe. In the far future, billions of years from now, an astronomer looking up from Earth would see only the Milky Way and its local group. The rest of the universe would have vanished beyond the horizon. The evidence for the Big Bang would be gone. The cosmic microwave background would be red-shifted into nothingness. We are living in a privileged time. We are living in the only era where the history of the cosmos is visible. This makes the data NASA is collecting now even more critical. It is a snapshot of the universe that will never be available again. But let us return to the edge itself. What does it look like? It does not look like anything. It is not a visual barrier. It is a gradient of fading light. As we look further out, galaxies become fainter, redder, and more sparse. Eventually, they dissolve into the background noise. The edge is a transition from signal to noise. It is the point where the information content of the light drops below the threshold of detection. With better technology, we can push the edge back. The James Webb Space Telescope has pushed the edge back further than Hubble ever could. It has seen galaxies that formed only a few 100 million years after the Big Bang. But even Webb has a limit. It cannot see through the fog of the early universe. It cannot see the moment of creation. The edge is also a temperature boundary. The cosmic microwave background represents a temperature of about 2.7 Kelvin. It is the afterglow of the hot, early universe. But this temperature is not perfectly uniform. There are fluctuations, tiny variations of 1 part in 100,000. These fluctuations are the seeds of all structure in the universe. They are the imprints of quantum variations stretched to cosmic scales. When NASA maps these fluctuations, they are mapping the edge of time. They are looking at the surface of last scattering. This is the closest we can get to the Big Bang. It is the wall of the prison. But what if the wall has cracks? What if there are patterns in the fluctuations that suggest something outside? This is the realm of topological defects, cosmic strings, domain walls, textures. These are theoretical structures that could have formed during phase transitions in the early universe. They could leave signatures in the cosmic microwave background. NASA has searched for these signatures. They have found some candidates, but nothing definitive. The search continues. The edge is not just a limit, it is a puzzle. And every piece of data we collect from the edge adds another piece to the puzzle. We must also consider the shape of the edge. Is the universe flat, open, closed? This determines the geometry of the edge. If the universe is closed, like a sphere, the edge curves back on itself. If it is open, like a saddle, it extends forever. If it is flat, it extends forever in a Euclidean sense. Measurements of the cosmic microwave background suggest the universe is flat, within a margin of error. This implies an infinite universe. If the universe is infinite, then the observable universe is just a tiny bubble in an endless sea. And if it is infinite, then everything that can happen does happen. There are infinite copies of you. There are infinite copies of Earth. There are infinite variations of history. This is the consequence of an infinite flat universe. But the measurement of flatness is not perfect. There is still a small uncertainty. The universe could be slightly closed. It could be a very large sphere. If it is closed, then the edge is an illusion. There is no edge. There is only the loop. But even if there is no geometric edge, there is still the observational edge. There is still the horizon, and that horizon is where the mysteries lie. That horizon is where NASA has focused its attention. Because beyond the horizon, the rules might be different. The constants of physics might be different. The laws of nature might be different. We cannot know. We can only infer. And the inferences are disturbing. The boundary of sight is also a boundary of knowledge. There are things we cannot know. There are questions we cannot answer. This is the hard limit of science. We are bounded by the speed of light and the age of the universe. We are bounded by the opacity of the early plasma. We are bounded by the acceleration of expansion. We are trapped in a cosmic island. And yet, within this island, we have built a civilization of understanding. We have decoded the light. We have measured the distance. We have weighed the stars. We have touched the edge with our minds, even if we cannot touch it with our hands. Chapter 2: The Echo of Creation. In 1964, 2 radio astronomers at Bell Labs in New Jersey were trying to calibrate a large horn antenna. They were not looking for the edge of the universe. They were trying to eliminate noise. Arno Penzias and Robert Wilson were plagued by a persistent hiss in their receiver. It came from everywhere. It did not change with the time of day. It did not change with the direction of the antenna. It was constant. They checked the equipment. They checked the connections. They even cleaned out pigeon droppings from the antenna, thinking the birds might be causing the interference. But the noise remained. It was a uniform background radiation filling the sky. At the same time, a team at Princeton University led by Robert Dick was predicting exactly this phenomenon. They theorized that if the universe began in a hot, dense state, there should be a remnant radiation left over, cooled by expansion to microwave wavelengths. When Penzias and Wilson heard about this, they realized what they had found. They had stumbled upon the cosmic microwave background. It was the echo of the Big Bang. It was the light from the edge of time. This discovery transformed cosmology from a field of speculation into a field of precision science. It provided the first hard evidence for the Big Bang theory. It gave us a snapshot of the universe when it was only 380,000 years old. But the initial discovery was just the beginning. The COBE satellite, launched by NASA in 1989, was the first to map this background radiation in detail. It confirmed that the spectrum was a perfect black body, exactly as predicted by the Big Bang model. But more importantly, it detected the anisotropies, the tiny fluctuations in temperature. These fluctuations were the seeds of galaxies. Without them, the universe would be smooth and featureless. Gravity needed these slight overdensities to pull matter together. COBE showed us the blueprint of the cosmos. It showed us the edge of the universe as a modeled sphere of heat and cold. WMAP, the Wilkinson Microwave Anisotropy Probe, launched in 2001, improved on COBE's resolution. It produced a much sharper image of the background radiation. It allowed scientists to determine the age of the universe with greater precision. It confirmed the composition of the universe: dark energy, dark matter, and ordinary matter. It showed that the universe is flat. It showed that the first stars formed about 200 million years after the Big Bang. WMAP took the blurry image of COBE and turned it into a high-definition map. It was like going from a sketch to a photograph. Then came Planck. The European Space Agency's Planck satellite, with significant NASA contribution, launched in 2009. It provided the most precise map of the cosmic microwave background to date. It resolved features down to a few arc-minutes. It refined the parameters of the universe. It adjusted the age to 13.8 billion years. It adjusted the expansion rate, the Hubble constant, but it also found anomalies. Anomalies that WMAP had hinted at, but that Planck confirmed. The universe is not as uniform as we thought. There is a hemispherical asymmetry. One side of the sky is slightly hotter than the other. There is a cold spot, a region of space that is significantly colder than the rest of the background. These anomalies are small. They are within the statistical noise, some argue, but others argue they are significant. They suggest that the standard model of cosmology, the lambda CDM model might be incomplete. They suggest that there is physics beyond our current understanding. The cold spot, in particular, has sparked intense debate. Is it a supervoid? A region of space with very few galaxies, which would cause the light to lose energy as it passes through, creating a cold spot via the integrated Sachs-Wolf effect? Or is it something more exotic? Some theorists have proposed that it is the bruise of a collision with another universe, a bubble universe that bumped into ours in the early moments of existence. If this is true, then the edge of our universe is not a boundary of nothingness. It is a boundary of contact. It is where we touch other realities. This is the concept of the multiverse. In eternal inflation theory, our universe is just one bubble in a frothing sea of inflating space. Other bubbles are forming all the time. Most are far away, never to interact with us. But occasionally, two bubbles might collide. The energy of that collision would leave an imprint on the cosmic microwave background. It would look like a disk of different temperature. The cold spot fits this description. It is not proof, but it is a hint. It is a whisper from the edge. The echo of creation is not just radiation. It is also gravitational waves, primordial gravitational waves. These are ripples in space-time generated during inflation. They would leave a specific polarization pattern in the cosmic microwave background, known as B modes. Detecting these B modes would be the smoking gun for inflation. It would tell us about the energy scale of the early universe. It would tell us about the physics of the edge. Several experiments have searched for these B modes. BICEP-2 claimed to find them in 2014, but it turned out to be dust in our own galaxy. The search continues. The edge is hiding its secrets well. The echo also tells us about the neutrinos, the cosmic neutrino background. Similar to the photons, neutrinos decoupled from matter even earlier, about 1 second after the Big Bang. They are even harder to detect. They pass through everything, but their existence is inferred from the effect they have on the structure of the universe. They affect the way galaxies cluster. They affect the expansion rate. NASA's data on galaxy distribution allows us to constrain the properties of these relic neutrinos. They are another layer of the edge, another messenger from the deep past. When we listen to the echo, we are listening to the sound of space itself. The fluctuations in the CMB are acoustic oscillations, sound waves traveling through the plasma of the early universe. When the universe became transparent, these sound waves froze. The pattern of peaks and troughs in the CMB power spectrum tells us about the density of the universe, the curvature, the composition. It is like listening to a bell ring and determining its shape and material from the sound. The universe rang, and the CMB is the recording of that ring, but the echo is fading. As the universe expands, the wavelength of the CMB photons stretches. They become lower energy. They become colder. In the future, they will be undetectable. The echo will silence. We are lucky to hear it now. We are lucky to have the technology to record it. The satellites like COBE, WMAP, and Planck are the microphones of the cosmos. They captured the voice of creation before it faded into the noise. And what they heard was complex. It was not a single tone. It was a symphony of fluctuations, a chaotic harmony that gave rise to stars and galaxies and life. The study of the CMB is the study of the edge. It is the study of the limit of our vision, but it is also the study of the beginning. The edge and the beginning are the same thing in cosmology. To look far is to look back. The surface of last scattering is the wall of the past. We cannot see through it. We can only see it. It is the horizon of history. And on that horizon, there are shadows. Shadows that might be other universes. Shadows that might be topological defects. Shadows that might be nothing at all. But the shadows are there. They are in the data. They are in the maps. They are waiting for us to interpret them. The echo of creation is the foundation of modern cosmology. It is the evidence upon which the Big Bang theory rests. Without it, we would be guessing. With it, we can measure, we can calculate, we can predict. But the anomalies in the echo suggest that our predictions are not perfect. There is more to the story. There is more to the edge. The echo is not just a record of the past. It is a clue to the future. It tells us about the fate of the universe. It tells us about dark energy. It tells us about the ultimate end. Will the universe expand forever? Will it collapse? Will it tear apart? The CMB holds the answers, encoded in its temperature fluctuations. We just need to decode them. Chapter 3. The Deep-Felled Portals. In 1995, the Hubble Space Telescope pointed at a patch of sky that was seemingly empty. It was a region near the handle of the Big Dipper. It was dark. There were no bright stars. There were no known galaxies. It was a void. The directors of the telescope decided to take a risk. They pointed Hubble at this spot and left it there. For 10 days, Hubble collected light. It opened its shutter and let the photons accumulate. It was a gamble. If there was nothing there, it would be a waste of precious telescope time. But if there was something, it would be revolutionary. When the image was developed, the world held its breath. The black spot was not empty. It was filled with galaxies, thousands of them. Every smudge of light was a galaxy. Some were spirals, some were ellipticals, some were irregular blobs. They were of different colors. Some were red, some were blue, some were close, some were far. The furthest ones were seen as they were when the universe was only a fraction of its current age. This was the Hubble Deep Field. It was a core sample of the universe. It showed that the universe is teeming with galaxies, even in the empty spaces. It showed that the edge of the universe is crowded. This observation changed our perception of the cosmos. It showed that the universe is homogeneous on large scales. No matter where you look, you see galaxies. But it also showed the evolution of galaxies. The galaxies in the deep field looked different from the galaxies nearby. They were smaller. They were more irregular. They were forming stars at a faster rate. This was evidence of galaxy evolution. We were seeing the ancestors of the Milky Way. We were seeing the building blocks of the modern universe. The deep field was a time machine. It allowed us to watch the history of the universe unfold. Hubble took more deep fields. The Hubble Ultra Deep Field in 2004, the Hubble Extreme Deep Field in 2012. Each one went deeper. Each one saw further. Each one pushed the edge back. The XDF saw galaxies that formed only 450 million years after the Big Bang. This was close to the edge of the observable universe. These galaxies were faint. They were red. They were small. But they were there. They proved that structure formed early. They proved that the universe woke up quickly. The deep fields are not just images. They are data sets. Each pixel contains information. Spectroscopy of the galaxies in the deep fields allows us to measure their redshift. Redshift is the stretching of light due to the expansion of the universe. The higher the redshift, the further away the galaxy is. By measuring the redshift of thousands of galaxies, we can construct a three-dimensional map of the deep universe. We can see the large-scale structure, we can see the cosmic web, the filaments of dark matter that connect the galaxies, the voids between the filaments. The deep fields reveal the skeleton of the cosmos, but the deep fields also reveal the limits of Hubble. Hubble sees invisible and ultraviolet light, but the light from the earliest galaxies is redshifted into the infrared. By the time it reaches us, it is no longer visible. Hubble is blind to it. This is why we needed the James Webb Space Telescope. Webb is an infrared telescope. It is designed to see the light that Hubble cannot see. It is designed to see the edge of the universe. The deep fields of Webb are already surpassing those of Hubble. They are seeing galaxies that formed even earlier. They are seeing the first stars. The concept of the deep field is a portal. It is a window into the past. When we look at a deep field, we are not looking at a place. We are looking at a time. We are looking at the universe when it was young. We are looking at the edge of history. And what we see there is surprising. We see galaxies that are too massive. We see stars that are too bright. We see structure that is too mature. According to our models, the early universe should be chaotic. It should take time for galaxies to form. But the deep fields show mature galaxies appearing very early. This is a tension in cosmology. It suggests that our understanding of galaxy formation is incomplete. The deep fields also show us the reionization epoch. This is the time when the first stars turned on and ionized the hydrogen gas in the universe. It cleared the fog. It made the universe transparent. The deep fields allow us to study this transition. We can see the galaxies that caused the reionization. We can measure their output. We can understand how the universe went from dark to light. This is a crucial chapter in the history of the cosmos. It is the dawn of the universe. And the deep fields are the only way we have to study it. But the deep fields are small. They cover a tiny fraction of the sky. They are like looking at the universe through a straw. To get a complete picture, we need wide fields. We need surveys. The James Webb Space Telescope is doing deep fields, but it is also doing wide surveys. It is mapping large areas of the sky. It is building a census of the early universe. This will allow us to understand the statistics of galaxy formation. Are the massive early galaxies rare, or are they common? If they are common, then our models are wrong. If they are rare, then we just got lucky with the deep fields. The deep fields also reveal the darkness between the galaxies. The intergalactic medium. It is not empty. It is filled with gas. Thin, hot gas. This gas absorbs light from the background galaxies. By studying the absorption lines in the spectra of distant galaxies, we can map the distribution of this gas. We can see the cosmic web in absorption. We can see the filaments of matter that feed the galaxies. The deep fields are not just about the galaxies. They are about the space between them. They are about the environment of the early universe. And what lies beyond the deep fields? What lies beyond the furthest galaxy? There is more universe. There are more galaxies. But they are too faint to see. They are beyond the sensitivity limit of our telescopes. They are beyond the edge of detection. but they are there. The deep fields show us that the universe continues. They show us that the edge is not a wall of galaxies. It is a fade into darkness, a gradient of density. The universe does not stop. Our vision stops. The deep fields are also a testament to human engineering. To capture these images, we had to build a telescope that could stabilize itself to within a fraction of a pixel. We had to build sensors that could detect single photons. We had to launch them into space, above the atmosphere, above the interference of Earth. We had to operate them remotely, millions of miles away. The deep fields are a triumph of technology. They are a monument to our curiosity. They are proof that we can reach out and touch the edge of the universe with our minds. But the deep fields also humble us. They show us how small we are. The Earth is a dot. The solar system is a dot. The Milky Way is a dot. In the deep field, every dot is a galaxy with billions of stars. And there are thousands of dots in a tiny patch of sky. Multiply that by the whole sky. The number of galaxies is incomprehensible. The number of stars is incomprehensible. We are insignificant, and yet we are the ones looking. We are the ones seeing. We are the universe observing itself. The deep fields are the mirror in which the universe sees its own face. Chapter 4: Infrared Eyes on the Dawn. The James Webb Space Telescope is not just a successor to Hubble. It is a different kind of eye. Hubble saw the universe in visible light. Webb sees it in infrared. This shift in wavelength is crucial. As the universe expands, light stretches. Visible light becomes infrared. Ultraviolet becomes visible. To see the earliest objects, we must see in infrared. Webb is designed for this. It has a large primary mirror, 6.5 meters in diameter. It is segmented, made of 18 hexagonal pieces of gold-coated beryllium. It folds up to fit inside the rocket, then unfolds in space. It is a marvel of engineering, but the mirror is only part of the story. Webb must be cold. Infrared is heat. If the telescope is warm, it will see its own heat instead of the heat from the distant galaxies. So Webb has a sun shield, a tennis court-sized shield that blocks the light and heat of the sun, Earth, and Moon. It keeps the telescope in permanent shadow. It keeps the instruments at minus 233 degrees Celsius. This allows Webb to detect the faint heat signatures of the first galaxies. It allows Webb to see the dawn of the universe. Webb launched on Christmas Day in 2021. It traveled to the second Lagrange point, 1.5 million kilometers from Earth. It unfolded its mirror. It cooled down, and then it opened its eyes. The first images were stunning. They were sharper than Hubble. They were deeper. They showed galaxies that Hubble missed. But the real science began with the deep fields. Webb looked at the Hubble ultra-deep field. It looked at the clusters of galaxies. It looked at the empty spaces, and it found things. It found galaxies at redshift 13. This means we are seeing them as they were only 300 million years after the Big Bang. These galaxies are bright. They are massive. They contain more stars than expected. This is the surprise of Webb. The early universe is not as dark and chaotic as we thought. It is bright and structured. The galaxies formed faster than our models predicted. This is challenging the standard model of cosmology. It is forcing us to rethink how stars and galaxies form. It is suggesting that the first stars were not just massive population 3 stars, but that they formed clusters quickly. Webb is also studying the atmosphere of exoplanets. It is looking at the edge of our own solar system in a way. It is looking at the potential for life. But in the context of the edge of the universe, Webb is looking at the chemical enrichment of the early universe. It is looking for heavy elements: carbon, oxygen, nitrogen. These elements are forged in stars. If we see them in early galaxies, it means stars, formed and died very quickly. It means the universe recycled matter rapidly. Webb is measuring the metallicity of the early universe. It is tracing the history of elements. Webb is also looking at the reionization epoch. It is trying to find the sources of reionization. Were it the first galaxies? Or were it quasars? Active black holes? Webb has the sensitivity to distinguish between them. It can measure the ionization state of the gas around the galaxies. It can map the bubbles of ionized hydrogen. This will tell us how the universe became transparent. It will tell us how the fog lifted. It will tell us about the end of the cosmic dark ages. But Webb has limitations. It is not infinite. It has a field of view. It has a sensitivity limit. It cannot see everything. There are galaxies beyond its reach. There is light beyond its wavelength. But it has pushed the edge further than any telescope before. It has given us a new view of the dawn. It has shown us that the universe is more vibrant than we imagined. It has shown us that the edge is not a barren wasteland. It is a nursery. It is where the stars are born. The infrared eye of Webb also sees through dust. Dust blocks visible light, but infrared passes through it. This allows Webb to see inside the clouds where stars are forming. It allows Webb to see the centers of galaxies, where black holes hide. It allows Webb to see the structure of the early universe without the obscuration of dust. This gives us a clearer picture of the edge. It removes the veil. It shows us the reality behind the haze. Webb is also working in tandem with other telescopes. It is working with Hubble. It is working with ground-based telescopes. It is working with the ALMA array. This multi-wavelength approach gives us a complete picture. Visible light shows the stars. Infrared shows the dust and the distant galaxies. Radio shows the gas. X-rays show the black holes. Together, they build a multi-dimensional map of the edge. They tell the full story. The data from Webb is vast. It will take years to analyze. Every image contains secrets. Every spectrum contains clues. The scientists are sifting through the data, looking for anomalies, looking for the unexpected, looking for the edge of understanding. And they are finding it. They are finding galaxies that should not exist. They are finding black holes that are too big. They are finding structures that are too old. The universe is full of surprises, and Webb is the one revealing them. The infrared eye is also a time machine. It sees the past, but it also sees the future. The technology developed for Webb will be used in future telescopes. Telescopes that will go even deeper. Telescopes that will see the first stars. Telescopes that will see the edge of the dark ages. Webb is a stepping stone. It is the bridge to the next generation of exploration. It is the prototype for the future of astronomy. But for now, Webb is the king of the edge. It is the most powerful telescope ever built. It is the most sensitive eye ever created. It is looking at the dawn of time. And what it sees is changing our understanding of reality. It is showing us that the universe is more complex, more dynamic, and more mysterious than we ever dreamed. The edge is not a limit, it is a frontier. And Webb is the explorer. Chapter 5: The Great Attractor's Shadow. We are moving. The Earth moves around the Sun. The Sun moves around the center of the Milky Way. The Milky Way moves through space. But what is it moving towards? In the 1970s, astronomers noticed that the galaxies in our local neighborhood were not just expanding with the universe. They had a peculiar velocity. They were flowing in a specific direction. They were being pulled. Something was pulling us. Something massive. Something hidden. This something was named the Great Attractor. It is a gravitational anomaly. It is a concentration of mass that is exerting a pull on our galaxy and thousands of others. It is located in the direction of the constellations Norma and Triangulum Australe. But there is a problem. This direction is behind the plane of the Milky Way. The disk of our galaxy is filled with dust and gas. It blocks our view. We cannot see the Great Attractor in visible light. It is hidden in the zone of avoidance. It is a shadow in the sky. For decades, the Great Attractor was a mystery. We could feel its gravity, but we could not see it. It was like a ghost. We knew it was there because of the motion of the galaxies. The local group, the Virgo cluster, and other nearby structures are all falling towards it. The speed is hundreds of kilometers per second. This requires a massive amount of gravity, a supercluster of galaxies. But what kind of supercluster, and why is it hidden? In the 1990s, astronomers used X-ray telescopes to peer through the dust. X-rays can penetrate the gas of the Milky Way. They found a cluster of galaxies behind the zone of avoidance, the Norma cluster. It was massive. It was dense. It was a candidate for the Great Attractor. But it was not enough. The gravity of the Norma cluster was not sufficient to explain the motion of the galaxies. There had to be more. There had to be something larger. Further studies revealed the Laniakea supercluster. In 2014, a team of astronomers mapped the flow of galaxies in our region. They defined the boundaries of our supercluster. They named it Laniakea, which means immense heaven in Hawaiian. The Great Attractor is located near the center of Laniakea. It is the gravitational focal point of our supercluster. All the galaxies in Laniakea are flowing towards it. We are part of this flow. We are falling towards the Great Attractor. But the Great Attractor is not the end of the story. Laniakea itself is moving. It is flowing towards another structure, the Shapley supercluster. This is even further away. It is even more massive. The gravity of Shapley is pulling Laniakea, and Laniakea is pulling us. We are part of a cosmic cascade of gravity. We are falling towards the Great Attractor, which is falling towards Shapley. The universe is a web of flows. We are caught in the current. The Great Attractor is a reminder that the universe is not static. It is dynamic. It is moving. The structures are evolving. The gravity is shaping the cosmos. But the Great Attractor also highlights the limits of our observation. It is hidden by our own galaxy. We are blind in that direction. We have to use indirect methods to see it. We have to use X-rays. We have to use infrared. We have to use radio waves. We have to infer its presence from the motion of other objects. This is the challenge of cosmology. We cannot always see the source. We have to see the effect. The shadow of the Great Attractor also raises questions about dark matter. The visible mass of the Norma cluster is not enough to explain the gravity. There must be dark matter. huge amounts of it. The Great Attractor is likely a node in the cosmic web where dark matter filaments converge. It is a knot in the net. It is where the invisible matter is densest. Studying the Great Attractor is studying dark matter. It is probing the invisible skeleton of the universe. But is the Great Attractor unique? Or are there others? Are there other attractors in other parts of the universe? The flow of galaxies suggests that there are. The universe is lumpy. Matter is not distributed evenly. There are clusters and voids. The gravity of the clusters pulls the matter from the voids. This creates the flows. The Great Attractor is just one example. It is the one closest to us. It is the one we can feel. But there are others, far away, pulling other galaxies. The study of the Great Attractor is also the study of our fate. Where are we going? We are falling towards the Great Attractor, but the universe is expanding. The expansion is accelerating. Will we ever reach it? Or will the expansion pull us away faster than we can fall? This is the battle between gravity and dark energy. Gravity pulls us together. Dark energy pushes us apart. In the local group, gravity wins. We will merge with Andromeda. We will fall towards the Great Attractor. But on larger scales, dark energy wins. The superclusters will be isolated. The flows will stop. The universe will tear apart. The Great Attractor is a symbol of the hidden universe. It is what lies behind the veil. It is what we cannot see, but we know it is there. We feel its pull. It is a reminder that there is more to the universe than what we see. There is mass we cannot detect. There are structures we cannot image. There is gravity we cannot explain. The edge of the universe is not just far away. It is also hidden. It is behind the dust. It is behind the light. It is in the shadows. And the shadows are deep. The zone of avoidance covers 20% of the sky. There could be other great attractors hidden there. There could be massive structures we know nothing about. We are mapping the universe, but the map is incomplete. There are blank spots. There are dark regions. The Great Attractor is the largest of these blank spots. It is the hole in our knowledge, and we are trying to fill it. We are shining light into the shadow. We are using every tool we have to see the unseen. The Great Attractor also tells us about the scale of the universe. It is millions of light years away. It is massive beyond comprehension. And yet, it is just a local feature. It is part of our neighborhood. Beyond it, there are larger structures. Beyond Laniakea, there are other superclusters. The universe is vast. The Great Attractor is just a stepping stone. It is a landmark on the journey to the edge. It shows us the way. It shows us the flow. It shows us the direction. But the direction is not simple. The flows are complex. They are turbulent. The galaxies do not move in straight lines. They orbit. They interact. They merge. The Great Attractor is not a single point. It is a region. It is a volume of space. It is a gravitational well, and we are falling into it, slowly, inexorably, until the dark energy takes over, until the expansion wins, until the edge moves away. Chapter 6. The Cold Spot Enigma. In the map of the cosmic microwave background, there is a blemish, a patch of sky that is colder than it should be. It is located in the southern hemisphere, in the direction of the constellation Eridanus. It is about 5 degrees across. It is significantly colder than the average fluctuations. It is an anomaly. It is the cold spot. When it was first discovered by the WMAP satellite, it was dismissed as a statistical fluke. The universe is random. There will be fluctuations. Sometimes they will be extreme. But when Planck confirmed it, the dismissal became harder. The cold spot is real. It is there. And it is strange. Why is it there? What caused it? The standard explanation is a supervoid. A void is a region of space with very few galaxies. It is empty. If there is a huge void between us and the CMB, the light from the CMB has to pass through it. As it passes through, it loses energy. This is the integrated Sachs-Wolf effect. The gravity of the void is weak. The light climbs out of the potential well and loses energy. It becomes red-shifted. It becomes colder, so a void could create a cold spot. Astronomers searched for a void in that direction, and they found one, the Eridanus supervoid. It is about 1.8 billion light-years across. It is huge. It is one of the largest structures ever discovered. It could explain the cold spot. But there is a problem. The size of the void is not enough to explain the temperature drop. The effect is too small. The void would need to be much larger or much emptier to create the cold spot. The math does not quite work. This leaves the door open for more exotic explanations. One of the most intriguing is the multiverse. In eternal inflation, our universe is a bubble. Other bubbles exist. If another bubble collided with ours in the early universe, it would leave an imprint. It would create a disk of different temperature on the CMB. It would look like a cold spot. The cold spot fits the profile of a collision signature. It is circular, it is distinct, it is anomalous. If this is true, it is the first evidence of another universe. It is the first proof of the multiverse. It is a bridge to another reality. The edge of our universe is where we touched another. The cold spot is a bruise from the collision. It is a scar on the face of the cosmos. This is a profound idea. It suggests that we are not alone, not just in the sense of life, but in the sense of existence. There are other universes, and we have seen the mark of one. But the evidence is not conclusive. It is circumstantial. It is based on models. It is based on theory. We cannot see the other universe. We can only see the effect. We can only see the cold spot. We have to infer the cause, and inference is not proof. Scientists are cautious. They do not want to claim a discovery without certainty. They want more data. They want better maps. They want to rule out the void explanation completely. There are other explanations too: cosmic textures, topological defects, strings. These are theoretical structures from the early universe. They could also create cold spots. They are like knots in the fabric of space. If light passes through a knot, it is distorted. It is cooled. The cold spot could be a texture. It could be a defect in the geometry of the universe. This would tell us about the physics of the early universe. It would tell us about the phase transitions. It would tell us about the symmetry breaking. But the multiverse explanation is the most popular. It captures the imagination. It fits the narrative of modern cosmology. The idea of infinite universes is common in theory. The cold spot gives it a face. It gives it a location. It makes it real. It moves the multiverse from math to observation. It moves it from speculation to data. This is why the cold spot is so important. It is not just a temperature anomaly. It is a potential window into the wider reality. The cold spot also challenges the cosmological principle. If the universe is homogeneous, there should not be such large anomalies. The The cold spot is too big. It is too cold. It is statistically unlikely. It suggests that the universe is not uniform. It suggests that there are preferred directions. It suggests that we are not in an average place. This is uncomfortable. It undermines the foundation of cosmology. It forces us to rethink the models. Scientists are studying the cold spot with other methods. They are looking at the galaxy distribution in that direction. They are looking for the void. They are measuring the density. They are checking the ISW effect. They are trying to confirm or refute the void hypothesis. So far, the void exists, but it is not enough. The mystery remains. The cold spot is still cold. The cold spot is also a reminder of the limits of our knowledge. We have mapped the CMB. We have measured the temperature. We have analyzed the fluctuations. And yet there is something we do not understand. There is a feature we cannot explain. The edge of the universe is hiding a secret. It is showing us a clue, but we cannot read it yet. We need more theory. We need more data. We need a new perspective. The cold spot is an enigma. It is a puzzle. It is a challenge. It is driving research. It is inspiring new ideas. It is pushing the boundaries of cosmology. It is making us look harder at the edge. It is making us question our assumptions. It is making us wonder, what if it is a collision? What if it is a texture? What if it is nothing? The uncertainty is the fuel of science. The cold spot is the fire. And the fire is burning. The debate continues. The papers are written. The conferences are held. The telescopes are pointing. The search for the truth goes on. The cold spot is not just a spot on a map. It is a symbol of the unknown. It is a mark of the edge. It is a sign that there is more to learn. It is a reminder that the universe is full of surprises. It is a whisper from the dark. Chapter 7: The Stretch of Space. The universe is expanding. This is the most fundamental fact of cosmology. Edwin Hubble discovered it in the 1920s. He saw that galaxies were moving away from us. The further they were, the faster they were moving. This implies that space itself is stretching. It is not that the galaxies are moving through space. It is that the space between them is growing. This is the expansion of the universe. But the expansion is not constant. It is accelerating. In the late 1990s, astronomers discovered that the expansion is speeding up. Something is pushing the galaxies apart. Something is overcoming gravity. This something is called dark energy. It is a mysterious force that permeates space. It has negative pressure. It repels. It drives the acceleration. It is the dominant component of the universe. It makes up about 68% of the energy density. The acceleration of expansion defines the edge of the universe. It creates the event horizon. Galaxies beyond a certain distance are receding faster than light. They are disappearing. They are moving beyond our reach. The edge is moving away from us. The observable universe is growing, but the reachable universe is shrinking. We are becoming more isolated. The acceleration is sealing us in. The stretch of space also affects the light. It redshifts it. It stretches the wavelength. It cools the radiation. This is why the CMB is cold. It was hot once, but the expansion cooled it. The stretch of space is the history of the universe. It is the record of time. By measuring the redshift, we can measure the age. We can measure the distance. We can measure the rate of expansion. But the rate of expansion is a problem. There is a tension. The Hubble constant. Different methods give different values. The CMB gives one value, the supernovae give another. They do not agree. This is the Hubble tension. It suggests that our model of expansion is wrong. It suggests that there is new physics. It suggests that dark energy is not constant. It suggests that the stretch of space is more complex than we thought. The stretch of space also affects the structure. It pulls the galaxies apart. It fights the gravity. In the early universe, gravity won, structure formed, galaxies clustered, but now dark energy is winning. The clusters are isolating, the filaments are stretching, the web is thinning, the universe is becoming emptier, the stretch is tearing the cosmos apart. This leads to the big freeze, the heat death. If the expansion continues, the universe will become cold and dark. The stars will die, the black holes will evaporate, the space will be empty, the edge will be everywhere. There will be no light, there will be no heat, there will be no life. This is the fate of the universe. The stretch of space leads to the end, but the stretch also creates the opportunity. It allows us to see the past. It allows us to see the edge. Without the expansion, the light would not be redshifted. We would not see the history. The expansion is the lens through which we view the cosmos. It is the mechanism of discovery. It is the tool of astronomy. The stretch of space is also a mystery. What is dark energy? Is it the cosmological constant? Is it a field? Is it a modification of gravity? We do not know. We only see the effect. We see the stretch. We see the acceleration. We see the edge moving. But we do not see the cause. The cause is hidden. It is in the vacuum. It is in the quantum fields. It is in the fabric of space. The stretch of space is the engine of the universe. It drives the evolution. It shapes the fate. It defines the edge. It is the most important force in cosmology. And yet, it is the least understood. It is the dark energy. It is the unknown. It is the mystery of the edge. The stretch also implies a beginning. If the universe is expanding, it must have been smaller in the past. It must have been dense. It must have been hot. This leads to the Big Bang. The stretch points to the origin. It points to the singularity. It points to the start of time. The edge of the past is the beginning. The stretch connects the beginning to the end. It connects the Big Bang to the Big Freeze. It is the thread of time. But the stretch is not uniform. There are variations. There are fluctuations. The expansion rate is not the same everywhere. There are local flows. There are gravitational wells. The stretch is modified by the matter. It is not a simple, smooth expansion. It is complex. It is turbulent. It is dynamic. The study of the stretch is the study of the edge. It is the study of the limit. It is the study of the fate. It is the study of the universe. And it is ongoing. The telescopes are measuring. The satellites are mapping. The scientists are calculating. They are trying to understand the stretch. They are trying to solve the tension. They are trying to find the cause. The stretch of space is the story of the universe. It is the narrative of cosmology. It is the plot of the cosmos. It is the arc of history. And we are living in the middle of it. We are watching it happen. We are measuring it. We are understanding it. We are the witnesses of the stretch. We are the observers of the edge. Chapter 8, Currents in the Cosmic Ocean. The universe is not still. It is flowing. The galaxies are moving. They are not just expanding, they are drifting. They are following the gravity. They are riding the currents of the cosmic ocean. These currents are the large-scale flows. They are the motion of matter on the grandest scales. One of these currents is the dark flow. In 2008, astronomers analyzed the motion of galaxy clusters. They found that they were moving in a specific direction. They were flowing towards a point outside the observable universe. They were being pulled by something we cannot see, something beyond the edge. The dark flow is controversial. Some scientists say it is real, some say it is an error. The data is noisy, the measurements are difficult. But if it is real, it is profound. It implies that there is matter beyond the observable universe. It implies that the edge is not the end. It implies that the universe extends beyond our horizon. And it implies that the matter beyond is influencing us. The dark flow could be caused by a massive structure outside our bubble, a supercluster beyond the edge. Or it could be caused by the multiverse, a collision with another universe, a gravitational pull from another bubble. The dark flow is similar to the cold spot. It is an anomaly. It is a hint of the beyond. It is a signal from the edge. The currents also include the rotation of the universe. Is the universe spinning? Some studies suggest a preferred axis, a cosmic axis of evil. This would violate the cosmological principle. It would mean the universe is not isotropic. It would mean there is a direction, a spin, a rotation. This is debated. The evidence is weak, but it is there. It is a whisper of rotation. The currents are driven by gravity. The overdensities pull the matter. The voids push the matter. The matter flows from the voids to the clusters. It creates the web. It creates the structure. The currents are the circulation of the cosmos. They are the blood flow of the universe. They keep it alive. They keep it dynamic. But the currents are slowing down. The dark energy is damping them. The expansion is smoothing the flows. In the future, the currents will stop. The galaxies will be isolated. The flow will cease. The ocean will be still. The universe will be dead. The currents are temporary. They are a feature of the early universe. They are a sign of youth, the study of. The currents is the study of the matter distribution. It tells us where the mass is. It tells us where the dark matter is. It tells us about the gravity. It tells us about the edge. The currents reveal the invisible. They show us the hidden mass. They show us the structure beyond the light. The currents are also a challenge to the models. The standard model predicts certain flows, but the observed flows are different. They are larger. They are faster. They are more coherent. This suggests that the model is incomplete. It suggests that there is more gravity, more mass, more structure. The currents are telling us that we are missing something. The cosmic ocean is vast. The currents are deep. We are floating on them. We are moving with them. We are part of the flow. We are not static. We are dynamic. We are evolving. We are traveling. We are on a journey through the cosmic ocean, and the destination is the edge. The currents also connect us to the past. They are the result of the initial conditions. They are the imprint of the Big Bang. They are the memory of the beginning. By studying the currents, we are studying the origin. We are studying the seed. We are studying the start. The currents are the motion of the edge. They are the dynamics of the limit. They are the life of the universe. And they are fading. They are dying. They are ending. The cosmic ocean is calming. The waves are settling. The flow is stopping. The edge is approaching. Chapter 9. Geometry of the Void. What is the shape of the universe? Is it flat? Is it curved? Is it closed? Is it open? This is the question of geometry. It is the question of the edge. The shape determines the fate. It determines the limit. It determines the nature of the void. Measurements of the CMB suggest the universe is flat. The angles of the triangles add up to 180 degrees. The parallel lines never meet. The space is Euclidean. This implies an infinite universe. It implies no edge. It implies forever. But the measurement has an error margin. The universe could be slightly curved. It could be closed, like a sphere. If it is closed, it is finite. It has a volume. It has a size. But it has no edge. You can travel forever and return to the start. It is unbounded. It is a loop. Or it could be open, like a saddle. It curves away. It is infinite. It expands forever. It is hyperbolic. It is complex. It is endless. The geometry is determined by the density, the critical density. If the density is high, the universe is closed. If it is low, the universe is open. If it is exact, the universe is flat. The measurements show it is exact. Within the error, this is the flatness problem. Why is it so flat? It requires fine-tuning. It suggests inflation. Inflation stretches the universe. It makes it flat. It smooths the curvature. It explains the geometry. The geometry of the void is also the geometry of the dark energy. The dark energy affects the curvature. It drives the expansion. It shapes the space. It defines the geometry. It is the architect of the void. The geometry also affects the light. It bends the light. It lenses the images. It distorts the view. By studying the distortion, we can measure the geometry. We can map the curvature. We can see the shape. We can feel the void. The geometry of the void is the structure of reality. It is the framework of existence. It is the stage of the cosmos. It is the container of the universe. It is the box of the edge. But the box might be infinite. It might be endless. It might be without boundary. It might be without limit. It might be without edge. The geometry tells us. The math tells us. The data tells us. The geometry is also the key to the multiverse. If the universe is infinite, there are infinite copies. If it is closed, there is one. If it is open, there are many. The geometry determines the multiplicity. It determines the reality. It determines the existence. The geometry of the void is the mystery of the edge. It is the question of the limit. It is the puzzle of the shape. It is the riddle of the space. And we are solving it. We are measuring it. We are calculating it. We are understanding it. The void is not empty. It is space. It is geometry. It is structure. It is form. It is shape. It is the universe. It is the edge. It is the everything. Chapter 10. The fading horizon. The edge is moving. It is receding. The galaxies are disappearing. The light is fading. The horizon is shrinking. This is the future of the universe. This is the fate of the observation. In the far future, the sky will be dark. The galaxies will be gone. The CMB will be cold. The evidence will be lost. The history will be erased. The edge will be invisible. We are living in the golden age of cosmology. We are living in the time of sight. We are living in the aura of light. But the light is fading. The expansion is accelerating. The horizon is moving away. The galaxies are crossing the line. They are vanishing. They are leaving us. They are going beyond the edge. They are entering the dark. The fading horizon is the end of science. It is the limit of knowledge. It is the closure of the window. It is the shutting of the eye. It is the silence of the universe. It is the death of the cosmos. But for now, the horizon is here. The edge is visible. The light is reaching us. The data is flowing. The telescopes are working. The scientists are watching. We are seeing the edge. We are touching the limit. We are knowing the universe. The fading horizon is a warning. It is a reminder. It is a call to action. We must observe now. We must record now. We must learn now. Before the light goes out. Before the edge disappears. Before the universe fades. The fading horizon is the story of the edge. It is the narrative of the limit. It is the plot of the end. It is the arc of the future. It is the fate of the sight. And we are the witnesses. We are the observers. We are the knowers. We are the ones who saw. We are the ones who measured. We are the ones who understood. We are the ones who looked at the edge of the universe. What NASA saw was not just data. It was history. It was reality. It was the universe. It was the edge. It was the everything. And it was fading. Chapter 11. The Architecture of Infinity. If the cold spot is indeed a bruise, a scar from a collision with another bubble universe, then the implications shatter our understanding of reality. We are no longer speaking merely of the edge of our observable universe. We are speaking of the edge of our entire existence. We are speaking of a multiverse. This is not science fiction. This is a mathematical consequence of the theory of eternal inflation. In this model, the Big Bang was not a unique event. It was a local event. Our universe is just one pocket in a much larger, eternally inflating cosmos. Space is expanding everywhere, all the time. But in certain regions, the inflation stops. Energy condenses into matter. Stars ignite. Galaxies form. Life emerges. These regions are bubbles. Our universe is one such bubble, but there are others, infinite others. Each bubble is a universe with its own laws of physics. In some, gravity is stronger. In some, light does not exist. In some, time flows backward. In most, nothing exists at all. They are dead bubbles. But some, like ours, are alive. And occasionally, these bubbles touch. When they do, the energy release is catastrophic. It would rewrite the laws of physics in both universes. But if the collision happened early enough, in the first fractions of a second, the evidence might remain. It might remain as a cold spot in the background radiation. It might remain as a distortion in the geometry of space. This theory changes the meaning of the edge. The edge is no longer a wall. It is a membrane. It is a surface tension between our reality and another. When NASA looks at the edge, they are looking at the skin of our bubble. They are looking for punctures. They are looking for leaks. They are looking for signs that we are not alone in the multiverse. This is the ultimate Copernican revolution. First, we learned Earth is not the center of the solar system. Then we learned the sun is not the center of the galaxy. Then, we learned the galaxy is not the center of the universe. Now, we are learning that the universe itself may not be the center of reality. We are nested. We are contained. We are part of a structure so vast it defies comprehension. But how do we test this? How do we prove the existence of something beyond our causal horizon? We cannot send a probe. We cannot send a signal. The space between the bubbles is inflating faster than light. We are causally disconnected. The only evidence we have is the fossil record. The cosmic microwave background is the fossil. It is the only artifact we have from the birth of our bubble. We must scrutinize it. We must look for patterns, circles within circles. disks of lower temperature, polarization anomalies. These are the signatures of a collision. Some scientists argue that the search is futile. They argue that if the collision was significant enough to leave a mark, it would have destroyed us. They argue that the universe is too uniform for such events. But the data disagrees. The universe is not perfectly uniform. There are anomalies. There are alignments. There are structures that suggest a preferred direction, the axis of evil, the cold spot, the dark flow. These are not just errors. They are clues. They are the cracks in the wall. They are the light leaking through from the other side. The architecture of infinity is a terrifying concept. It implies that everything that can happen does happen. There is a universe where you never existed. There is a universe where humanity never evolved. There is a universe where the earth never formed. There is a universe where the laws of physics are slightly different and stars never ignite. The multiverse is a library of all possibilities, and our universe is just one book on one shelf. The edge of our universe is the cover of that book. When NASA looks at the edge, they are reading the cover. They are trying to see the title of the next book. But there is a cost to this knowledge. If the multiverse is real, then our universe is not special. It is not unique. It is not chosen. It is just one of many. This is a humbling realization. It strips away the last vestige of centrality. We are not just insignificant in space, we are insignificant in reality. We are a statistical accident, and yet we are the ones asking the question. We are the ones looking at the edge. We are the ones trying to read the cover. In a multiverse of infinite dead bubbles, we are the ones who woke up. We are the ones who see. That makes us special, even if our universe is not. The search for the multiverse continues. New satellites are being proposed. New methods of analysis are being developed. We are looking for the shadow of another universe on our wall. We are looking for the echo of a collision. We are looking for the edge of the bubble. And if we find it, if we confirm it, it will be the greatest discovery in human history. It will change our philosophy. It will change our religion. It will change our understanding of existence. It will tell us that the edge is not an end. It is a doorway. But for now, it remains a hypothesis. It remains a mathematical possibility. It remains a dream. But it is a dream based on data. It is a dream based on the cold spot. It is a dream based on the anomalies. It is a dream that NASA is chasing. They are chasing the edge of reality. They are chasing the infinite. And they are getting closer. The instruments are getting better. The maps are getting sharper. The noise is getting quieter. And the signal is getting clearer. The architecture of infinity is revealing itself, slowly, painfully, beautifully. Chapter 12. The Invisible Scaffold. While we look for bubbles, beyond the edge, we must also look at the structure within it. The universe is not just filled with light, it is filled with darkness. Dark matter. It makes up 85% of the matter in the universe. It does not emit light. It does not absorb light. It does not reflect light. It is invisible, but it has gravity. It holds the galaxies together. It forms the scaffold upon which the visible universe is built. When NASA looks at the edge, they are not just seeing light. They are seeing the shadow of dark matter. We know it is there because of the way galaxies rotate. They spin too fast. The visible mass is not enough to hold them together. They should fly apart, but they don't. Something is holding them, something invisible. We know it is there because of gravitational lensing. Light from distant galaxies bends around massive objects, but sometimes it bends around nothing. It bends around empty space. That empty space is filled with dark matter. It is a lens made of shadow. When NASA maps these lenses, they are mapping the dark matter. They are seeing the invisible scaffold. This scaffold extends to the edge. The cosmic web is made of dark matter. The filaments that connect the galaxies are dark matter. The voids between the clusters are defined by dark matter. The edge of the universe is not just a limit of light. It is a limit of gravity. It is a limit of mass. And the mass is mostly dark. This means that what we see is only a fraction of what is there. The edge is darker than we think. It is heavier than we think. It is more complex than we think. The distribution of dark matter tells us about the history of the universe. It tells us about the initial fluctuations. It tells us about the growth of structure. It tells us about the nature of gravity. If dark matter behaves differently than we think, if it interacts with itself, if it decays, it would change the shape of the edge. It would change the distribution of galaxies. It would change the lensing patterns. NASA is looking for these deviations. They are looking for cracks in the dark matter model. They are looking for new physics. There are theories that dark matter is not a particle. It is a modification of gravity, modified Newtonian dynamics, MOND. If this is true, then there is no dark matter. There is just a different law of gravity at large scales. This would change everything. It would change the edge. It would change the mass. It would change the fate. But the evidence favors dark matter. The lensing is too specific. The fluctuations in the CMB are too precise. The scaffold is real. It is made of something. We just don't know what. The search for dark matter is the search for the hidden edge. It is the search for the majority of the universe. We are living in a minority universe. The visible matter is the foam on the wave. The dark matter is the water. We are studying the foam and ignoring the ocean. NASA is trying to dive beneath the surface. They are building detectors deep underground. They are building sensors in space. They are trying to catch a dark matter particle. They are trying to touch the invisible. If we find it, if we identify it, we will understand the edge. We will understand why the galaxies are where they are. We will understand why the universe is structured the way it is. We will understand the scaffold. But until then, the edge remains partially hidden. It remains shrouded in darkness. We see the lights on the scaffold, but we don't see the scaffold itself. We see the cities, but not the land. We see the stars, but not the gravity. This invisibility is a challenge. It limits our knowledge. It limits our models. It limits our predictions. We are navigating a map where most of the terrain is blank. We are sailing an ocean where most of the water is invisible. But we are doing it. We are mapping the shadows. We are weighing the darkness. We are defining the edge by what we cannot see. This is the paradox of modern cosmology. To see the edge, we must look for the dark. To understand the light, we must study the shadow. The invisible scaffold also connects us to the beginning. The dark matter was there at the Big Bang. It was there before the first star. It was there before the first galaxy. It is the primordial substance. It is the foundation. When we look at the edge, we are looking at the foundation of reality. We are looking at the base of the structure, and it is dark. It is cold. It is silent. But it is there. It is holding everything together. It is holding us together. Without it, we would not exist. The galaxies would not exist. The stars would not exist. We are guests in a house built of darkness. Chapter 13. The Vanishing Point. There is a tragedy in the edge of the universe. It is not just that we cannot see beyond it. It is that what we can see is disappearing. The expansion of the universe is accelerating. The galaxies are moving away from us. They are moving faster and faster. Eventually, they will move faster than light. They will cross the event horizon. They will vanish. They will be gone forever. This is the vanishing point. This is the future of the edge. In 100 billion years, the sky will be different. The distant galaxies will be gone. The cosmic microwave background will be red-shifted into nothingness. It will be too cold to detect. The evidence for the Big Bang will be lost. An astronomer in the future will look up and see only the Milky Way. They will see only the local group. They will see only the darkness. They will not know about the expansion. They will not know about the Big Bang. They will not know about the edge. They will think the universe is static. They will think the universe is small. They will think they are alone. We are living in a privileged era. We are living in the only time when the history of the universe is visible. We are living in the golden age of cosmology. We can see the edge. We can see the past. We can see the evidence. But this window is closing. It is closing faster than we thought. The dark energy is pushing the galaxies away. It is erasing the history. It is wiping the slate clean. The edge is receding. The light is fading. The information is being lost. This is a cosmic censorship. The universe is hiding its origins. It is hiding its structure. It is hiding its edge. Why? We don't know. Is it a coincidence? Is it a necessity? Is it a design? We don't know. But it is happening. The vanishing point is approaching. The galaxies are slipping over the horizon. They are dropping out of sight. They are entering the dark. And we are watching it happen. We are watching the universe disappear. This adds urgency to our work. We must record what we see. We must map what we can. We must save the data. Because in the future, it will be all we have. It will be the only record of the cosmos. It will be the only proof that the universe was ever vast. We are the archivists of reality. We are the keepers of the light. We are the ones who saw the edge before it vanished. This is our responsibility. This is our duty. We must not let the knowledge die. The vanishing point also changes the meaning of the edge. The edge is not just a place. It is a time. It is a deadline. It is the limit of our opportunity. We have a limited time to understand the universe. After that, it will be too late. The evidence will be gone. The questions will be unanswerable. The edge will be unreachable. We are racing against the expansion. We are racing against the dark energy. We are racing against the vanishing point. This is a melancholy thought. It suggests that knowledge is temporary. It suggests that understanding is fleeting. It suggests that the universe does not want to be known. It is hiding from us. It is moving away from us. It is closing the door. But we are still here. We are still looking. We are still trying. We are still pushing against the vanishing point. We are still gathering the light. We are still saving the history. We are still defining the edge. The vanishing point is the fate of the observer. It is the fate of the scientist. It is the fate of the species. We will be alone in the dark, but we will know. We will know what was there. We will know what was lost. We will know the edge, and that knowledge will be our legacy. It will be our monument. It will be our proof that we were here, that we saw, that we understood. Even if the universe forgets, we will remember. We will keep the record. We will keep the map. We will keep the edge. Chapter 14, The Mirror of the Cosmos. Why do we look? Why do we care about the edge? Why do we build telescopes? Why do we launch satellites? Why do we spend billions to see what is billions of light years away? What does it matter? It does not feed the hungry. It does not cure the sick. It does not stop the wars. So why do we do it? Because we are human. Because we are curious. Because we need to know. The edge of the universe is a mirror. When we look at it, we see ourselves. We see our limitations. We see our potential. We see our place. The edge tells us that we are small. It tells us that we are brief. It tells us that we are fragile. But it also tells us that we are capable. We can comprehend the infinite. We can measure the unimaginable. We can see the beginning of time. We are the universe observing itself. We are the eyes of the cosmos. We are the mind of the universe. Without us, the edge would exist, but it would not be seen. It would not be known. It would not be understood. We give the edge meaning. We give the universe consciousness. This is the philosophical consequence of the edge. It is not just a physical boundary. It is a cognitive boundary. It is the limit of our mind. When we push the edge back, we are pushing our mind back. We are expanding our understanding. We are growing our consciousness. We are becoming more than we were. We are becoming cosmic. We are becoming universal. We are becoming part of the edge. The edge also tells us about our loneliness. We have not found life. We have not found signals. We have not found friends. The universe is silent. The edge is quiet. This is the Fermi paradox. Where is everybody? The edge suggests that we are alone, or that life is rare, or that civilizations destroy themselves, or that they hide. Whatever the answer, it is profound. It means we are responsible. We are the only ones we know of. We are the only ones who can care. We are the only ones who can protect. We are the custodians of life. This responsibility is heavy. It is burdensome, but it is necessary. We must survive. We must expand. We must continue. We must keep looking. We must keep pushing the edge. We must keep asking the questions. Because if we stop, if we die, if we fade, the universe will lose its voice. It will lose its observer. It will lose its meaning. We are the meaning. We are the purpose. We are the reason the edge is seen. The mirror of the cosmos reflects our drive. It reflects our hope. It reflects our fear. It reflects our wonder. When NASA looks at the edge, they are looking at us. They are looking at our history. They are looking at our future. They are looking at our soul. The data is not just numbers. It is a story. It is our story. It is the story of how we came to be. It is the story of how we came to know. It is the story of how we came to look. The edge is not outside us. It is inside us. It is in our minds. It is in our dreams. It is in our questions. We carry the edge with us. We carry the universe with us. We are the container. We are the vessel. We are the boundary. When we understand the edge, we understand ourselves. When we see the limit, we see our potential. When we touch the void, we touch our own depth. This is why we look. This is why we care. This is why we build. Not for the data, not for the science, not for the knowledge, but for the meaning, for the connection, for the understanding, for the reflection. The edge is a mirror, and we are looking into it. We are seeing ourselves. We are seeing our place. We are seeing our purpose. And we are not turning away. We are staring into the abyss, and the abyss is staring back. Conclusion: what NASA saw at the edge of the universe was not a wall. It was not a barrier. It was not an end. It was a beginning. It was a horizon. It was a limit of light, but not a limit of reality. It was a boundary of sight, but not a boundary of existence. They saw the cosmic microwave background. They saw the cold spot. They saw the deep fields. They saw the great attractor. They saw the dark flow. They saw the stretch of space. They saw the invisible scaffold. They saw the vanishing point. They saw the mirror. They saw a universe that is vast, a universe that is old, a universe that is complex, a universe that is mysterious, a universe that is hiding, a universe that is fading, a universe that is alive. They saw that we are small. They saw that we are brief. They saw that we are alone. They saw that we are capable. They saw that we are curious. They saw that we are necessary. The edge is not a place we can reach. It is a place we can know. It is a place we can understand. It is a place we can feel. It is the limit of our knowledge. It is the horizon of our understanding. It is the boundary of our reality. And it is moving. It is receding. It is fading. It is vanishing. But we are here. We are now. We are seeing. We are knowing. We are understanding. This is the legacy of NASA. This is the legacy of science. This is the legacy of humanity. We looked at the edge. We saw what was there. We recorded what we found. We shared what we learned. We passed the torch. We kept the light. We defined the boundary. We mapped the void. We touched the infinite. The journey is not over. The edge is still there. The mysteries are still unsolved. The questions are still unanswered. The cold spot is still cold. The view of the dark flow is still flowing. The dark matter is still dark. The multiverse is still theoretical. The vanishing point is still approaching. There is more to see. There is more to know. There is more to understand. But we have started. We have begun. We have looked. We have seen. We have found. And that is enough. For now, for this moment, for this era, we have seen the edge of the universe, and we have not looked away. We have stared into the deep dark, and we have found light. We have found knowledge. We have found ourselves. What NASA saw was everything. It was the history of creation. It was the structure of reality. It was the fate of the cosmos. It was the meaning of existence. It was the edge. And it was beautiful. It was terrifying. It was profound. It was true. The script ends here. But the observation continues. The telescopes are still pointing. The sensors are still collecting. The scientists are still analyzing. The edge is still waiting. It is waiting for us. It is waiting for the next question. It is waiting for the next discovery. It is waiting for the next look. We will not stop. We cannot stop. We must not stop, because the edge is calling. And we must answer. We are the ones who saw. We are the ones who know. We are the ones who understand. We are the ones who looked at the edge of the universe. And we will look again, and again, and again, until the light fades, until the edge vanishes, until the universe is silent, until the end. We will be there. We will be watching. We will be seeing. We will be knowing. We will be human. This is the story of the edge. This is the story of NASA. This is the story of us. It is a story of curiosity. It is a story of courage. It is a story of hope. It is a story of light in the dark. It is a story of life in the void. It is a story of meaning in the mystery. It is a story of the edge. And it is our story.